반갑습니다. H2 미트 컨퍼런스 2024 테크 토크의 진행을 맡은 아나운서 김지영입니다. 반갑습니다. 네, 오늘 가을비가 내리고 또 선선한 기분 좋은 바람이 불어오는 이렇게 좋은 가을날 여러분들 모시고 행사를 진행할 수 있게 되어 진심으로 영광으로 생각합니다. 바쁘신 가운데 귀한 시간 내셔서 H2 미트 컨퍼런스 2024 본 행사에 힘을 실어주시기 위해 이렇게 자리해 주시고 또 자리를 빛내주고 계시는 참가자 여러분들께 깊은 감사의 말씀 드립니다. 여러분이 함께하고 계시는 테크토크는 수소 생산부터 저장, 운송, 활용까지 이어지는 수소산업 밸류체인의 최신 기술 정보를 공유하고 또 글로벌 수소산업의 최신 기술 동향을 파악할 수 있는 세션입니다. 본 프로그램은 9월 25일부터 27일까지 총 3일 동안 Utilization, Production, Fuel Cell, Storage and Distribution 이라는 총 4개의 주제로 진행이 되며 오늘은 2일차를 맞이하게 되었습니다. 그럼 지금부터 H2 Meet 컨퍼런스 2024 토픽 2 세션을 시작하겠습니다. 토픽 2의 주제는 Frontiers of Hydrogen Advancements in Fuel Cells and Production 이며 총 5개의 강연이 20분씩 진행이 될 예정입니다. 각 강연이 끝난 후 질의응답 시간을 이용해서 질문이 있으신 분들께서는 질문해 주시면 되겠습니다. 네, 그럼 가장 첫 번째로 AP Green Incorporation의 Chief Technology Officer이신 알리티 라이시 님께서 Hydrogen from Methane via NTP-POX Process라는 제목으로 강연을 진행해 주시겠습니다. 네, 여러분 큰 박수로 맞이해 주시기 바랍니다.
Thank you very much for your attention. I am Ali Raisi. I am CTO of Upgrade. I appreciate you showing up for the presentation. I have kind of a little long presentation, so I apologize if I kind of run through some of the slides that are busy. It's needless to say that methane in the form of natural gas is used by many countries, many places. Of course, Korea is no different, and Korea, in fact, is one of the top 3 importers of LNG. LNG's role in South Korea's energy strategy is very prominent, and the government, as you can see in this slide, has implemented mechanisms to minimize the cost of transition to hydrogen. I must say that methane is viewed as a transition fuel on its way to hydrogen. Kind of very busy. The bottom line on this slide is that everybody needs a new and innovative technology to address our need for developing alternatives to fossil fuels and reducing the carbon emission. Korea is no different. Korea has commitment as part of the Paris Conference to reduce its carbon footprint. And these are some of the statistics here. Some of them might be a little bit dated, as government has changed some of them, modified it. But the bottom line is even Korea may be a little bit behind in meeting the requirements of the Paris Conference. Therefore, we are trying to do our part in developing cutting-edge technology to reduce the carbon footprint for Korea as well as other countries and other markets. Our approach, our cutting-edge approach involves using non-thermal plasma in the form of dielectric barrier discharge and using this technology in conjunction with partial oxidation to reduce the, or pretty much eliminate carbon dioxide formation. Now, why it is valuable? Because it is well known that methane itself is a very greenhouse gas, very powerful greenhouse gas, much more potent than carbon dioxide itself. So being able to take fossil fuel that is itself very potent greenhouse gas and convert it to hydrogen, which is a clean fuel, without emitting any CO2, will be a very useful technology. And that's the aim of the work at Upgrade. However, there are many technologies. They do carbon capture in many different ways. Some of them are capturing physically CO2 and removing it for storage. Others converting it to useful chemicals like methanol, okay? Which then you have to worry about what happens to that carbon when methanol is used itself as a carbon, as a fuel. Our approach is to capture CO2 in the form of a solid. You may not know about carbon oxides, there are more carbon oxides than carbon monoxide and carbon dioxide. Carbon suboxide that you can see here is a solid and can be easily collected as a part of the storage and collection and storage effort. So our activity at Upgrade, our technology involves extracting CO rather than CO2 and then converting it to C3O2, which is a solid. So that's the approach that we are taking in our technology. This is the prototype that we have built and is being optimized for its methane production as well as for its hydrogen production as well as no carbon dioxide emission at Upgrade. Okay, this is a pretty busy slide, but the bottom line here is the technology is a marriage between partial oxidation and non-thermal plasma. The non-thermal plasma produces carbons that act as a catalyst for the partial oxidation. Now, partial oxidation is a very well-known technology, but the problem with it is that most of the catalysts that are used, mostly transition metal catalysts, do deactivate during the process. And there is a good deal of effort on finding catalysts that do not deactivate. Okay. Carbon is one of those. And the carbon that is produced by NTP appears to be active in partial oxidation reactions. Okay, this again summarizes what I just told you. Carbon capture in methane oxidative reformation by generating carbon suboxide and collecting that instead. This is the structure. This is the upgrading process layout, which starts with partial oxidation, methane and oxygen or air. Actually, air is preferred because nitrogen in air is an excellent plasma gas. that we're gonna need it here, right there. So reaction between these two forms syngas. Hydrogen is extracted here. CO is directed to non-thermal plasma, which converts it to C3O2. And the CO2 is generated in the process, goes through the reverse water gas shift reaction, produces CO recycled here, and hydrogen is pumped out. Just like everybody else, we do work on the flow sheeting our process and optimizing in activity. Aspen is one of several platforms that we use. We use also DWSIM as well as ChemStation. I show you the result for the ChemStation. I am not expecting you to read anything here, just that emphasize that we have simulated using ChemStation a process of producing 5,000 kilogram per day hydrogen from methane. Capital costs of the system are discussed here. As you can see, we envision the process being modular, each module generating 80 kilogram per day of hydrogen, and then you have these modules parallel to each other to produce higher quantities. Now, why 80 kilogram per day? It seems to be based on availability of the hardware, especially ancillaries for the system, and ease of production and handling. So all the capital costs are based on all the, I apologize. Thank you. This is much better. Works fine. Thank you. As you can see, all of the calculations for the cost estimates are done originally for 80 kilogram per day, and then we multiplied it to get 5,000 kilogram per day hydrogen. And these are the breakdown of the unit ops and the simulation costs. This is numbers that are evaluated by the chemical process simulator, by the way. Although some of them are based upon our own data collection from real world values of how much these different systems cost at this level. To give us the capex of about $2 million, $2.2 million for 5,000 kilogram per day hydrogen for refueling station. OPEX involves evaluating the feedstock cost, that is given here, utility cost, which is electricity to run the non-thermal plasma system. Non-thermal plasma system roughly consumes 2% of the overall energy contained in the hydrogen that is produced in the process. And the heavy lifting of the breakdown of the methane, reformation of it, is carried out in the POX reactor using an internal reaction between methane and oxygen, essentially very close to autothermal reaction. Because it is more efficient, energy released internally, there is no need for energy to be transferred from outside, and heat transfer issues goes away. If you are careful with the design of the reactor, so there is no hot spots developing, that turns out to be the best way to carry out the oxidation of CH4. These are the assumptions are made for maintenance and repairs to give you the capital operating cost of a $5,000, 5,000 kilogram per day hydrogen to be roughly $1.2 million per annum. Based upon the simulation results and a laboratory test, for a 500 kilogram per day, which might be more appropriate for a small fueling station. I don't know how to go back. Oh, yeah. For the estimated energy efficiency turns out to be 83% for the 500 kilogram per day, based upon the platform calculation I showed you earlier. Okay, then the question is what the profit and loss values are. Well, they depend upon where you market the hydrogen. In one scenario that we have done, and I show you here, is in California, because California has very generous credits for hydrogen production and avoidance of greenhouse gas. Some of those indexes and values are shown here. I just skip that and give you my final slide, I believe, to give you the economic assumptions made and profit and loss. As you can see, with California's very generous credit, we can make a lot of, we can make a respectable revenue in the process. He's my CEO of the company, and thank you very much. If you have questions, sorry for running over, and also sorry for running over some of the slides very quick. Yes, any questions?
Thank you very much for your presentation. So now let's see if we have questions from the floors. 질문이 있으신 분께서는 자리에서 손을 들어주시면 마이크를 전달해 드리도록 하겠습니다.
Crystal clear, I suppose.
So maybe they want to visit your booth to discuss more in details. Thank you very much once again, and please return to your seat.
We have a booth here. If you are interested or there is any more question, please stop by, and I will go over all of those figures in more detail and give you more information about the system that we have. We have a prototype here that you can look at. Thank you very much. Thank you for your attention.
Thank you. 네, 큰 박수 부탁드립니다. 감사합니다. 네. AP 그린의 수소 제조 공정에서 드는 비용 그리고 규모 등 다양한 유익한 정보를 공유해 주셨습니다. 감사합니다. 그럼 다음으로는 내셔널 피지컬 라보라토리의 시니어 사이언티스트이신 디팍 비제쿠마 신대님께서 강연을 해 주시겠습니다. 강연 제목은 Insight to Reference Electrodes as Diagnostic Tool for Water Electrolyzers입니다. 여러분 큰 박수로 환영해 주시기 바랍니다.
Hello everyone, good morning. It's nice to be back in Korea again. So my name is Deepak. I'm a senior scientist at UK's National Physical Laboratory, and I'm going to talk about how you can lower down cost of your electrolyzers. A brief introduction to NPL. NPL is UK's National Metrology Lab. Metrology here refers to measurement science and not the other thing about environment. So we are a public research institute founded in 1900, and we are responsible for maintaining national measurement standards and developing new measurement techniques. Well, then you'll think what institute like NPL is doing in a hydrogen space, as we are a measurement institute. Well, if you want to improve something, you need to measure it accurately, whether it's a kind of device or any property. And that's what we do in hydrogen space. We develop accurate measurement techniques for hydrogen devices such as electrolyzers, fuel cells, to understand their performance and durability. And we work with several companies, as mentioned there. We participate in European projects. We work with academia, and we work with government and standard bodies to develop measurement standards. So coming to hydrogen in the UK, in 2021, UK announced its hydrogen strategy. Essentially, they say that by 2013, UK wants to have about 10 gigawatts of hydrogen capacity. Next, I'll talk about what we do in hydrogen space at NPL. As I mentioned, again, we work on electrochemical hydrogen technologies such as fuel cells, water electrolyzers, proton pumps. To understand their performance and durability, we develop measurement standards and new measurement techniques. We also work on hydrogen gas quality. Our gas lab is one of the best lab in the world in terms of developing measurement standards and highly accurate measurement techniques. Of course, as you may know, hydrogen is again a potent greenhouse gas. So we work on developing accurate measurement techniques to measure hydrogen in the atmosphere. And we work on, of course, hydrogen materials, components that you use in your hydrogen devices, to develop accurate measurement techniques. Standards. Now coming back to water electrolyzers, I'm going to say is CapEx. Of course, companies want to lower down their CapEx, and how so it can be done by, say, reducing the cost of the components that you use, and that component development process is going on since a long time. Academia and industries are involved in intensive research efforts to produce optimized components that are high performance and stable. However, unfortunately, more than 90% of measurements for these components are done in a very small scale laboratory setups, which are not representative of true conditions experienced by those components in, say, large devices or industrial scale devices. And that's why a lot of research, academic research, just falls in this valley of death. It never sees light of the day, and it never reaches the scale application. And that's why we propose studying devices in situ. What it means is that you prepare a device that is representative of what the device will actually look like in an industrial setting, and then you put analysis probes, for example, in this case, a reference electrode inside the device, and then you measure the property that you want to improve or you want to know more about. So our first work relates to putting a reference electrode in a proton exchange membrane electrolyzer. So in a proton exchange membrane electrolyzer stack, porous transport layer mentioned there and bipolar plate form significant make up the largest contribution to the cost of the stack, and that's because platinum coated titanium is used as a material for bipolar plates and current collectors because of its stability in corrosive environments. So it's assumed that on the anode side, because of high potentials and acidic conditions, you need to have a stable material or a noble metal coating for it to be stable under those conditions. Well, we prove otherwise. So what we did, we put a reference electrode probe near the current collector. So this is a typical lab scale proton exchange membrane cell. And with this probe, we show that the current collector does not experience the corrosive conditions. It stays at its open circuit potential, so it does not experience corrosive potentials. And therefore, you can replace your current collector with cheaper materials, maybe stainless steel. We went one step further and we put further more reference electrodes inside the porous transport layers at different depths, as shown here in one of the example. And with this, we also developed a model to show that, so typically proton exchange membrane water electrolyzers operate, need pure water, so either it's type 1 or type 2 water. And this model shows that in type 1 and type 2 water, so this is a distance from your anode catalyst layer, and as you move away from your anode catalyst layer, the voltage immediately drops to its open circuit potential, so it's no longer corrosive environment for the materials. And our measurements kind of validated the model, which are shown here. So in air contaminated type 1 water, which is about 20 microsiemens per centimeter, you can see that the voltage drops immediately after the anode layer. So within like 150 micrometers, the voltage is already non-corrosive for the components. And based on these results, we propose a new model or new kind of device architecture for PEM electrolyzers, where so this is a conventional design. So instead of this, we propose to replace part of PTL, all the mesh and the bipolar plate with carbon coated stainless steel instead of platinum coated titanium, which is shown here. So you need only very thin layer of platinum coated titanium near the anode catalyst layer, where it experiences the corrosive potential. But after that, you can get away with materials such as carbon coated stainless steel. Now, so this was about OPEX and how you can lower your cost of your PEM electrolyzer. Now going to OPEX of electrolyzers, and electricity cost is your major kind of contribution to your OPEX. And electricity cost relates to the voltage at which your electrolyzers operates at. Lower the voltage, lower the electricity cost you are going to incur, and lower the OPEX. So for this, what we did again is design and develop this kind of PEM electrolyzer cell, about 4 square centimeter active area, and we put reference electrode on both anode and cathode sides. So in order to lower the voltage and therefore the capex, the OPEX, you need to understand how and what each part in your electrolyzer cell is contributing to the voltage. So with this, we show that your anode and cathode, so cathode, typically platinum carbon particles contribute only about 100 millivolts to your cell voltage, whereas anode, so anode and cathode combine only about, say, 1.5, 1.55 volts, and the rest is coming from your membrane, separator membrane that is used. So with this kind of, so again going back to the cell architecture, so with this kind of cells, if you develop new material for your stack, you'd be able to accurately measure its performance, and therefore would be able to optimize your device based on the results you get from, say, voltage contribution from each of the layer in your electrolyzer cell. So the conclusion of our work is that in order for to make rapid progress in materials development for electrolyzer, everyone wants to lower the cost of their technology, and customers are looking for whatever the cheaper technology or cheaper device you can get in the market. So in order to make this rapid progress in material development, low cost materials, the measurements needs to be done at representative conditions, and that this kind of reference electrode probe is a good way to understand the voltage contribution or say voltage losses in your operating electrolyzers. So yeah, if you need more information or wants to work with NPL, so we provide testing and validation of your hydrogen devices, electrolyzers, fuel cells, proton pump, or gas mixtures. Please scan the QR code. And yeah, thank you very much. That's it from me.
Thank you very much for your presentation. Now, please wait for the Q&A session. 네, 질문이 있으신 분께서는 자리에서 손을 들어주시기 바랍니다. 네, 질문이 없으시면 다음 강연으로 넘어가 보도록 하겠습니다. Thanks once again, and please return to your seat. 네, NPL이 수소 관련해서 진행하고 있는 업무들을 소개해 주시고 또 수전해줘야 되는 비용 삭감을 위해서 또 레퍼런스 전극을 어떻게 활용하고 있는지 잘 공유해 주셨습니다. 네, 그럼 잠시 휴식 시간을 가져볼 텐데요. 잠시 후 오전 11시 25분부터 이어서 세션을 진행해 볼 테니 잠시 편안하게 휴식 시간 취하시고 잠시 후에 다시 뵙도록 하겠습니다. 감사합니다.
The shift towards a decarbonized society is accelerating. H2 represents hydrogen and humanity, the two main pillars of Hyundai's hydrogen business, leveraging the group's wide-ranging capabilities in various sectors beyond automobiles. Hyundai's H2 vision spans across the entire hydrogen value chain, from production to its utilization across industries. Hydrogen fuel cell technology brings significant advantages, like extended range and fast refueling capabilities. The H2 fuel cell system, created through more than 20 years of research and development, represents Hyundai's commitment to creating a new wave for a hydrogen society. Clean energy based on hydrogen, paving the way for a sustainable future.
When you think about net zero aspirations, you need lower carbon systems that can work in the process and the heat that we need to work with. Hydrogen, from that perspective, is a very versatile molecule in the energy transition. It has applicability in the transport sector, especially in heavy duty transport, where we can use it with existing combustion engines or with fuel cells. But it can also be used as a direct combustible fuel in industrials like cement and steel. These are big investments, and they offer big potential for lowering risk and carbon intensity for all kinds of consumers and companies. Chevron is uniquely positioned to lead the way forward.
We're a fully integrated energy provider enabling new energies for a growing world. And because we are Chevron, we have an opportunity to lead the way.
편안한 휴식 시간 보내셨길 바라면서 다시 테크토크 세션을 이어가 보겠습니다. 먼저 연사분들께서는 원활한 동시 통역 제공과 또 매끄러운 내용 전달을 위해서 마이크를 가까이 서서 진행해 주시면 감사하겠습니다. A reminder for speakers, for a smooth simultaneous interpretation and clear delivery, please speak closely to the microphone. Thank you. 네, 그럼 다음 강연 소개해 드리도록 하겠습니다. 이번 강연은 특별히 두 분의 연사분들께서 준비해 주셨는데요. 세레스의 Chief Scientific Officer이신 닥터 슈비 무커지님과 두산 필셀의 Director of Strategy이신 고우영님께서 Working in Partnership to Deliver Solid Oxide Fuel Cell Technology라는 주제로 함께 강연을 진행하시겠습니다. 네, 여러분 큰 박수로 환영해 주시기 바랍니다.
Good morning. Good morning, everybody. Thank you for the introduction. And let me just first start by saying it's a real pleasure to be here at the Hydrogen Meet. I'm Shubhi Mukherjee from Ceres Power. And it's also a real pleasure to give this talk with our partner in Korea, Mr. Ko from Doosan. I will tell you a little bit about our technology and some of the key features and the benefits of our technology. And Mr. Ko will tell you about the fantastic job that Doosan has done to take our technology into mass manufacture and develop products here in Korea. A little bit of an introduction here. I'm the Chief Scientific Officer at Ceres, and I've been at Ceres from 2012. When I joined Ceres, we were about 50 people, and now we are 500 and growing. I also am a visiting professor at Imperial College London, and also I've worked in this field for a very, very long time. And who are we at Ceres? So we are one of the leading developers of solid oxide technology in the world. We have a unique technology, and I'll tell you a little bit about it. It can be used for fuel cells and for electrolyzers. And we have lots of patent families, and we have a unique business model that we license our technology to partners all around the world. And today you will hear how Doosan, one of our main partners, has taken this technology and are developing it in Korea for different products. We collaborate, as I said, with world-leading companies, and that's the model we have to take this technology into the market at scale and at pace. So at Series, we developed this technology for both fuel cells, for power, as well as for green hydrogen, so electrolyzers. And one of the benefits of our technology is you can use it, the same materials, the same designs for both of these applications. Obviously, key to our technology is a repeating unit, which is the solid oxide cell. You see it there in the bottom left, and I'll talk a little bit about that core building block. And multiples of those are made into a stack, which also is our very proprietary design, which is very mature, very robust, and low cost. There are huge advantages of using our technology. We are very highly efficient in fuel cell as well as in electrolysis mode. We are fuel flexible in fuel cell mode. I'll show you some of the fuels we can use. We are metal supported. That's very unique to our technology, and very sustainable materials. And we are cost efficient and modular and scalable. And you will see that in some of the products that Doosan is making with our technology. So at the core of our technology or our offering is a metal supported cell which can operate at low temperatures compared to other high temperature solid oxides. So that makes it two big advantages. Number one, it's very robust and it is low cost. And we have class leading robustness and low temperature performance due to this metal supported design, and fundamentally lower material cost and sustainable materials, which are allow for a very, very cost-effective proposition. Now, the robustness is not only robustness to vibration, but robustness to thermal cycling, robustness to emergency stops, all of the things that makes it into very good products for both fuel cells and electrolyzers. So the key layers in our fuel cells are shown here. We have a 300 micron ferritic steel, which is basically the backbone to our cell. And then we have different layers of ceramics. The fuel electrode consists of Syria nickel cermet, a gadolinium doped Syria-based electrolyte that allows this to be operated at the lower temperature, and a perovskite-based air electrode. Because we use gadolinium doped Syria, we have an electron blocking layer and a CGO barrier layer between the air electrode and the electrolyte. All of this is very core to our technology. We own the IP and the processes. They're all manufactured by high volume manufacturing processes, as well as it's key to note that there is no precious metals or semi-precious metals in this core technology. And also, just like the core technology, we also have very innovative design for the stacks and a lot of experience in making the stacks. We used to make the 1 kilowatt, which then went into the 5.7 kilowatt, and now we have roughly a 10 kilowatt offering, which is very mature, low cost, and obviously we've made improvements in current density, and we have about 300 layers in this. Overall, through many of our customers, we have a lot of experience in running these stacks at different systems, and over 500,000 hours that we've accumulated. So a lot of experience and maturity of our product that our customers are then taking and manufacturing in high volume. Now, as I said, in fuel cells, we are fuel flexible, and so we can obviously use hydrogen when the hydrogen economy is there. But for now, we can use methane or natural gas, or a blend of hydrogen with natural gas or methane. We obviously can use biogas after cleanup, and obviously e-methanol And ammonia is another very interesting fuel that we are working on for marines, and there's a lot of application there, and LOHC, which is also being talked about as potential fuel in marines. Compared to other fuel cells like PEM, we are much more tolerant to some of the hydrocarbon impurities and other impurities, which in some cases like CO, but for us CO is actually a fuel. So that's one of the advantages of using our technology for different fuel cell applications. And just like we use our fuel cells for multiple applications like commercial power, distributed power, or shipping, like I said, you can also use our technology and our products for electrolysis. So using renewable energy and making green hydrogen for hard-to-abate sectors, which is very difficult to decarbonize, you can use this technology. And one of the advantages of this technology, it's 20 to 25% more efficient than other conventional electrolysis technologies like alkaline or PEM. And some of the applications we think will be in green steel, decarbonizing ammonia, the Haber-Bosch process, and in future fuels like, for example, e-fuels, e-methanol, as well as sustainable aviation fuel, all of which are absolutely critical for our economies to meet net zero. And with the same technology and the same stack designs, we are meeting the needs for multiple markets in the fuel cell sector, which you see at the top, with Doosan, Bosch, and Weichai. And today, Mr. Ko will tell you some of the fantastic work that's going on in Korea with Doosan, a fantastic partner for us. But also in the electrolysis mode, we are working with many different companies. So we are having demonstration projects with Shell, with Linde, and Bosch. But also, our technology for electrolysis has been licensed by Delta and also now with Denso. So a lot of licensees all around the world taking our technology, and today's focus will be with Doosan, who is working with us on taking this for products here in Korea. And as you can see, for electrolysis, just like for fuel cells, we have to scale, and we are working with the designs to scale it up to 100 megawatt and gigawatts of a plant with other players like EPCs who are looking at that. One of them is Atkins, and so if you're interested in electrolysis, we can give you designs that allow for this to be scaled up and applied all around the world. And also in the fuel cell mode, we are working with our partners to scale up. So Doosan scaling up to 600 kilowatt, with Bosch to hundreds of kilowatt, and with Weichai similarly to megawatts. So with this, I think you've got an understanding of our technology, the key benefits, and how it can be applied. And I will hand it over to my partner, Mr. Ko, from Doosan.
네, 세레스의 인상 깊은 발표 잘 들었고요. 닥터십께 감사드립니다. 안녕하십니까. 저는 두산 퓨얼셀에서 전략 팀장을 맡고 있는 고우영이라고 합니다. 저는 오늘 기술 본연에 대한 얘기보다는요, 기술이 어떻게 프로덕트에 반영되고 이것이 마켓에 나올 수 있는지 그 관점에서 두산 퓨얼셀의 비즈니스에 대해서 간략하게 설명드리겠습니다. 두산 퓨얼셀을 말씀드리기에 앞서서 두산 그룹의 수소 사업에 대해서 간략히만 말씀을 드리겠습니다. 일일이 열거하기 어려운 다양한 사업들을 두산 에너빌리티, 주식회사 두산의 자회사들, 그리고 하이엑시온과 두산 퓨얼셀이 각자의 강점들을 살려서 특화된 분야에서 사업을 진행하고, 그 와중에 시너지를 낼 수 있는 분야에 대해서는 적극적으로 협력을 하고 있습니다. 이 모든 사업의 기반에는 두산 그룹의 강점이 기반이 되고 있는데요. 그 강점은 바로 두산 에너빌리티를 중심으로 트래디셔널 에너지와 리뉴어블 에너지에서 쌓아왔던 다양한 경험들, 그리고 전자소재나 기계설비와 같은 영역에서의 풍부한 제조 경험, 그리고 그 과정에서 글로벌 다양한 파트너들과 쌓았던 네트워크, 이를 바탕으로 두산 그룹에서의 수소 사업이 전개되고 있습니다. 특히 두산 퓨얼셀은 주식회사 두산의 미국 자회사인 하이엑시온과 긴밀한 협조하에 PAFC, SOFC, 페미C 등의 주요 연료전지 라인업을 모두 갖추고 글로벌 수소 종합회사로 발돋움을 하고 있습니다. 두산 퓨얼셀의 하이드로젠 비즈니스의 역사입니다. 사실 뭐 두산 퓨얼셀 올리는 아니고요. 하이엑시온과 그 전신이었던 미국의 UTC 파워 인수되기 전의 역사까지 모두 포함한 것입니다. 뭐 하나하나 다 얘기를 드릴 부분은 아니고요. 제가 말씀드리고 싶은 부분은 현재 여기 표현된 2024년까지 PAFC에 기반으로 진행되었던 사업들은 저는 페이즈 1이라고 표현을 하고 싶습니다. 그리고 이 맵 안에 표현되지 않는 25년부터 저희가 세레스와 협력하에 새로운 SOFC 제품이 본격적으로 양산되는 2025년부터가 두산 퓨얼셀 하이드로젠 비즈니스의 뉴 페이즈라고 정의를 내리고 싶습니다. 그래서 이 아래에 표현된 60여 년의 경험, 수많은 정량적인 성과들은 페이즈 2에서는 전혀 다른 새로운 양상으로 새롭게 히스토리를 써나갈 것입니다. 바로 그 페이즈 2의 핵심 자산이 돼 저희 생환금 SOFC 공장의 모습입니다. 그리고 주요 마일스톤을 말씀드리고자 합니다. 2024년 3월까지는 건축물에 대한 건축이 끝났고요. 그리고 이 완공된 건물 안에서 주요 제조 라인들의 설비가 일부 설치가 되고 있고 대부분의 설비는 설치가 되어서 커미셔닝 그리고 양산을 준비하는 파일럿 프로덕션이 진행이 되고 있습니다. 그리고 아까 말씀드렸던 25년 4월까지의 공정 최적화가 마무리된 이후 2025년 5월부터는 본격적인 매스 프로덕션에 진입을 하게 됩니다. 연 생산 캐파시티는 50메가와트 규모로 운영이 될 예정입니다. 방금 말씀드렸던 SOFC 시스템의 본격적인 양산을 통해서 두산 퓨얼셀은 퓨얼셀 비즈니스에서 포트폴리오를 한층 강화하게 됩니다. 기존에 저희가 갖고 있었던 PEFC 기술로서는 클린 힛을 만들 수 있었고 그리고 유연한 개통 대응을 통해서 일부 장점을 가지고 있었지만 새롭게 런칭되는 SOFC 시스템을 통해서는 타 SOFC 대비해서 탁월한 스택의 내구성 그리고 분산 전원, 독립 전원에 안정적으로 전원을 공급할 수 있는 능력 특히 초기 효율이 전기 효율이 65%에 달해서 감히 업계 최고 수준이라고 자부할 수 있습니다. 그리고 새로 개발된 SOFC 시스템에는 유지보수를 용이하게 하는 핫스왑 방식이 적용되어서 한층 더 진보된 기술로 고객의 만족을 더할 수 있을 것으로 기대됩니다. 이를 통해서 기존에 저희가 영위했었던 유틸리티 스케일 그리고 분산 전원에서의 사업 영역 거기에서 더 나아가 현재 수요가 급증하고 있는 데이터 센터의 전력 공급 그리고 중장기적으로는 세레스의 메탈 소프트 기술이 가장 크게 빛을 발하게 될 선박용 SOFC 연료전지 시장에서 저희의 프레전스를 높여갈 예정입니다. 여기서 시장을 잠깐 짚고 넘어가고 싶습니다. 역시 문제는 시장입니다. 안타깝게도 대부분의 현존하는 연료전지 기술들이 시장이 요구하는 LCOE를 만족하지는 못하고 있습니다. 그래서 단기적으로 저희도 CHPS를 통해 수소의 생산과 활용을 촉진하고 있는 국내 정책 기반으로 사업을 꾸려나가고자 합니다. 다만 오른쪽에 표현이 되어 있듯이 올해 시행이 된 분산에너지 특별법에 기반해서 구체적으로 연료전지에 적합한 규제들과 지원 정책들이 새로 수립이 된다면 새로운 사업 기회를 확보할 수 있을 것으로 예상을 하고 있습니다. 그리고 자료에는 표현을 하지 못했지만 국내뿐만 아니라 중국, 대만 등의 아시아 지역 그리고 하이엑시온과의 공조를 통해서 미국 시장에 침투하는 전략을 세우고 있습니다. 네, 현재 진행형으로 이루어지고 있는 두산 퓨얼셀의 SOFC 개발과 설치에 관한 몇 가지 내용들만 공유를 드리고 마치고자 합니다. 첫 번째 보시는 내용은 약 2주 전에 보도자료로 공표가 되었는데요. 두산 그룹 내 SOFC 시스템 설계를 전담하고 있는 두산 H2 이노베이션이라는 회사와 그리고 한수원 등이 협력해서 국책과제로 한국형 중저온 SOFC의 실증 운전을 시작했습니다. 2000시간의 운전을 목표로 하고 있고 이 기간을 통해 한국형 SOFC의 가능성을 시험받게 됩니다. 다음은 본격적으로 저희가 외부에 공표는 안 했는데요. 최초의 SOFC 제품이 공급돼 첫 프로젝트의 계약이 성사가 되었습니다. 현재 시점에서는 고객과의 관계 등으로 인해서 구체적인 내용들을 말씀드릴 수는 없지만 이 사이트에는 저희 기존에 갖고 있었던 PAFC 제품과 SOFC 제품이 믹스가 되어서 최초로 시도되는 PAFC, SOFC 통합 발전소의 모습을 띠게 될 것입니다. 그리고 마지막으로 좀 전에 말씀드렸던 선박용 SOFC입니다. 저희는 현재 글로벌 선사인 쉘 그리고 한국조선해양 등과 함께 선박용 SOFC 실증을 위한 공동 프로젝트를 수행하고 있습니다. 올해까지 선박에 탑재가 될 예정이고요. 내년부터는 실제 선박이 운항을 하게 되고 그 운항하는 가운데 저희 SOFC 제품이 운전을 하게 되고 그를 통해 안전성과 성능 등을 입증하게 될 예정입니다. 이상으로 제가 준비한 내용은 마치겠습니다. 마지막으로 저희의 핵심 자산이 될 군산 공장의 2년여간의 건축 과정을 짧은 영상으로 소개해드리고 마치겠습니다.
네, 좋은 발표 감사합니다. 네, 그럼 이어서 질의응답 시간을 가져볼 텐데요. 질문이 있으신 분께서는 자리에서 손을 들어주시기 바랍니다. 네, 질문이 없으시면 다음 강연으로 넘어가 보도록 하겠습니다. 네, 좋은 발표해 주신 두 분께 다시 한번 큰 박수 부탁드립니다.
Thank you very much.
네, 세레스의 연료전지 기술 특징과 또 적용 사례 그리고 두산과의 협업 내용을 공유해 주셨습니다. 네, 다음으로는 헤레우스 프레셔스 메탈스 GmbH and Corporation KG의 크리스찬 브로이어 님, 글로벌 테크놀로지 앤 어플리케이션 매니저이신 크리스찬 브로이어 님께서 강연을 해 주시겠습니다. 강연 제목은 A Holistic Approach to Fuel Cell Balance of Plant, Catalyst and Adsorbents to Boost the System Performance입니다. 네, 여러분 큰 박수로 환영해 주시기 바랍니다.
All right. So many thanks for the kind introduction and for the opportunity to present here today. I think the presentation before was a perfect link to the topics I will be talking about, because I will be talking about components that go into fuel management systems, or respectively exactly those balance of plant catalysts and materials that will facilitate the operation of the fuel cell. So, but before I go into this topic, just one step back. Just a quick introduction about the company. So Heraeus Precious Metals, it's a global leader in precious metals. And basically this precious metal cycle here on the right-hand side is at the core of our business, namely the recycling, the refining, then the generation of innovative precious metal-based products, bring them to the markets and take them back and start this cycle again, accompanied by our trading services, especially for these precious metals given here on the left lower left corner. And this, of course, sprouts a lot of or broad portfolio of different components for the hydrogen economy. And with my last presentations here in Korea, I have, for example, been focusing on in a presentation about the PEM electrolysis catalysts, where we use our ruthenium and iridium materials, or our platinum and palladium-based gas purification catalyst for oxygen and hydrogen purification. And of course, I've been talking a lot about our catalysts for the ammonia cracking. So today, I will rather be focusing on what we put here under reforming and purification catalysts for SOFC and hydrogen generators, which are in basically the reconversion and use segment, as how we see it. And what this means for us is basically this, and there's a quite complex network of very different functions. For example, you see on the right-hand side, there are options that start, if you look at the different fuels, not only natural gas, but also like newer fuels or hydrogen storage media like ammonia or methanol, which help to, in a first degree, upgrade these materials to make them processable, for example, for the reforming catalysts. And then, of course, the reforming and pre-reforming is a very important step in this process. And followed then, depending on what quality you need and what gas composition your fuel cell will be needing, with different purification and polishing steps, as well as getter components that help to protect the stack and the material behind that. I will today, let's go back once again. Can I go back? No, I cannot go back. Anyway, I will today not focus on like the purification system for like grade D hydrogen for like PEM or to inject into the grid. This will be something I will be happy to discuss you at our booth here. I will today focus exactly on the SOFC, and this is, I just put down the advantages and disadvantages of the system, but I think you had a very good first-hand degree description from Ceres just a few moments ago, so I will not go into detail here. But the general message is the same. The SOFC systems, they have a very high efficiency and durability goal. And however, these materials, they're quite unique and they are really, really durable and resilient and robust in their operation. But nonetheless, even these robust high temperature operating stacks of an SOFC are to some degree subject to deactivation and deterioration mechanisms. There are on the one hand, of course, the things that like the stack designers have to solve, which are the intrinsic deactivation mechanisms like delamination, cation segregation, material agglomerations and such. But there are also other things that originate from external sources. And this is especially like coking, sulfur poisoning, silica poisoning, chromium poisoning, and depending on what fuel you use, possibly also nitridation. And those are exactly these topics we tackle with the balance of plant components and try to get the stack into a like robust, smooth operation. And then we look again at the sources. There once again for these external sources are then fully external sources for these poisons like sulfur, oxygen, unsaturated hydrocarbons, longer chain hydrocarbons that all could cause trouble in the stack operation. And then there are also in-system emissions like silica or chromium that can get into the stack and then cause troubles in operation, especially with regards to durability. And this is where we set on with the balance of plant components. In this case here, this is basically just a more detailed view on the slide I gave you before, and basically shows how different components can work together. We have the partial oxidation catalyst that could help with, especially for example with natural gas in the system startup. We have, I mentioned already, the fuel upgrading catalysts, which could additionally help in sulfur absorption. We have hydrogenation catalysts that help in pre-processing the fuel. We have catalysts for oxygen removal. I will tell you later some example where this could be critical. And then of course we have the different reformer systems. Pre-reformers for natural gas, for LPG. We can use ammonia pre-crackers. We can use methanol reformers. And then, of course, additional to the pre-reformers are also like the classic main reformers, especially for the SMR, for example, like classic steam methane reforming options. And then, on the outlet side, there are the tail gas oxidation catalysts for the anode off-gas oxidation. But on the inlet, there are then the getter materials that prevent or should prevent silica or chromium that is forming in the system to get into the stack. You see already by these pictures we've chosen for these individual components that we can offer these components based on our portfolio not only like as a classic bulk material, but coated on different substrates and different geometries. And then by the choice of the substrate and the component, we can further enhance the properties of the catalytic or the adsorbing material. For example, by applying filter materials, or by applying coated honeycombs, or specifically applying bulk materials for different questions and requests of the system behind it. And further, we can offer these technologies also as coatings on, for example, existing hardware components, and by this further enhance the functionality and also maybe help with the energy integration to the full system. I haven't mentioned yet, this is something we don't do just by ourselves, but we have a strategic cooperation with the company Hulteberg Chemistry Engineering in Sweden, and both by the combined portfolio with Hulteberg having already more than a decade of experience, we can very much support you in selecting the right components and also selecting the right material. In the following minutes, I will give you just some examples on how these things play together and for what reasons some of these components are important. I will work my way through really quickly from like a cold operation further to the hotter operation closer to the stack. And so how these, basically the components then protect the operation of their following downstream components. There's a nice example here, for example. This is for oxygen removal. If, for example, if you have a biogas, you can have traces of oxygen in this gas. And then if you would go with this in a reformer, in a pre-reformer, this is something this downstream component doesn't like at all, especially if you're using a nickel reformer catalyst. So, to protect this, ahead of this, we use oxygen removal catalysts that basically oxidize react with the hydrocarbons. And then there's a nice study that's not been done by us, but by a university in Karlsruhe, but they had been using some catalysts we provided, which really nicely shows you the activity profiles of the catalyst, and especially nice the use of platinum and palladium. Then, what I really like about this study is they didn't just stop there, but they also studied the sulfur deactivation of these catalysts, which of course sulfur components, if you look at biogas for example, is always something you have to be aware of. And they could very much show that depending on the degree of sulfur, the concentration of sulfur in, you end up with different deactivated states. Something to be considered. So here the catalyst serves also like as a sulfur catcher, but of course this it should not. So ideally these components are even better removed upstream of the system. But there are also some sulfur components that are hard to catch in these applications. So for these applications, we have in the portfolio specific sulfur absorbents, to be precise, that will help to catch also other trace components, which I said we have long durability targets, will also accumulate in the system over time, and they are designed to operate like in at moderate temperatures. And here we did a stress test showing that by combination of different getter materials, we get, this is shown in the lower graph, a very nice time of protection. So now considering that the actual concentrations of these are between 100 and 1,000 times lower than we did in the stress test, or the conditions of the stress test, we can basically show that we can buy, with these materials, the system some further time to protect it from sulfur poisoning. And then downstream of that, there we have the saturation catalysts. Why use a saturation catalyst? The saturation catalyst here, operating here nicely in a temperature window around 200 to 300 degrees C, is there to specifically saturate ethylene and propylene. Because if those stay in the gas and go into the pre-reformer will coke and lose its activity, and then basically in the end the main reformer will lose its activity, and then in the end the stack might undergo troubles with coking prematurely. And then we use these saturation catalysts and basically protect the whole downstream system by converting them to higher hydrocarbons. And then this brings us directly to the next system, is the main reforming catalyst, or the pre-reforming catalyst in this case. You see, pre-reforming catalysts, we have very different options. We have nickel-based options, we have ruthenium-based options, which I know are quite popular here. But we also have rhodium-based options. And I know rhodium is always a bit tricky in terms of the material prices, but this rhodium catalyst we have here is a real workhorse. And I would very much like to present this here, because not only is it very durable and very efficient, but it also allows us to tailor its properties specifically. So depending on what the stack needs, or gas mixture, how much methane the stack can allow with its operation, or how much hydrogen it needs, we can choose of different materials. And here, this is a very nice study we did on these materials, where we have to consider that those have the two types we show here, the PRC and the PRCH, have the same precious metal loading, but very much differ in their activity towards methane reforming. So we can pick a material that either supplies the stack with a methane-rich or a less methane-rich material, while nonetheless very efficiently getting rid, which is the main target of the pre-reformer, of the higher hydrocarbons. And this is a very nice example on how, with the materials we supply, we can tailor them to specific properties. Of course, this is just an add-on. Of course, rhodium, I mentioned, is of course a valuable material, but depending on the conditions and the best we understand the overall system conditions, we have shown in studies that with these materials, compared to the workhorse formulation I just showed you on the previous slide, for example, in other applications could go to operations with, in this case, 75% less rhodium than the previous one, and still reach the desirable operation regime. So understanding the material will also help, and understanding the system will also help improve the material efficiency here. Another important topic is the getter materials, and I mentioned that chromium and silica poisoning can be challenging for the operation of a stack. And so we can apply specific getter materials to the upstream components that could either help as an evaporation barrier, for example, for chromium, or get these materials from the gas stream. And then you see as well, we can apply them on different geometries as filters or as code on hardware to then exactly perform these tasks before the chromium, which is there's a common mechanism. It can basically evaporate from a lot of components in the stack. It's postulated as this type before this one reaches really the cathode. This is important not only for SOFC, but could also be an important feature to apply with an SOEC application, for example. And then this is just something on tail gas oxidation catalyst. I will skip through this a bit quicker because it is basically drives on the challenges we've encountered also with our emission catalysts since quite some time. I want to show you something else because we've also been talking about ammonia as a fuel and the operation of ammonia systems. And here the idea is, of course, you use ammonia as a transport medium and then directly use it in such a direct ammonia SOFC without any pre-treatment or anything. And basically the idea is that ammonia cracks into hydrogen and nitrogen directly in situ in the anode chamber. Nice idea. I am a bit reluctant with this process because the cracking reaction where it takes place also contributes to nitridation of a lot of steel components. And it just shows some pictures here that were taken from some ammonia operating where we see that these materials can deteriorate under the operating conditions. And so our proposal is to rather use a pre-cracking catalyst for the ammonia ahead of the stack instead of going directly in. But of course, this is dependent on the individual operation of the system in a way. However, just to continue, just to show, I mean, this is ammonia cracking I mentioned in the beginning is a topic for us since quite some time. And we've been also like focusing on the industrial process, but also on pre-cracking options for ammonia fuels. And then could basically, in some studies, this is like for a combustion engine with a German engineering company, did some case studies and also compared ruthenium and nickel and could really show that with our ruthenium coatings, we can make a difference for these pre-cracking systems as well. This is something we look as a precious metal company, of course, on the ruthenium on different angles, so you can look at this as well. And basically, just as a closing statement, we can support you in your projects with our lab capabilities, both in the our partners in Sweden as well as in at our labs in Germany, and also can run different test series specific to your operations, and then can, of course, also support your whole commercialization process with the services we offer. And this, now we're going to close. These are the different geometries we can make. And then I would very much like to invite you to our booth for a follow-up discussion. We are at E51. And of course, we have these materials. There's an overview brochure we offer with contact details. I would very much like to continue this discussion then there at our booth. Thanks a lot.
Thank you very much for your informative presentation. And let's see if we have questions from the floor. 네, 질문이 있으신 분께서는 자리에서 손을 들어주시기 바랍니다. 네, 없으시면 부스로 방문하셔서 질문 시간 가져보시면 좋을 것 같습니다. Thanks again and please return to your seat. 네, 감사합니다. 네, 이어서 핀란드의 탐페레 유니버시티의 프로페서이신 무하메드 임란 아쉬가 님께서 Smart Manufacturing of Reversible and Solid Oxide Fuel Cells for Hydrogen Production and Electricity Generation 이라는 제목으로 강연을 진행하도록 하겠습니다. 네, 여러분 큰 박수로 환영해 주시기 바랍니다. 네, 자료 확인 문제로 잠시만 1분 정도만 대기해 주시면 감사하겠습니다. Now they are checking the materials,
The material, yeah.
so please wait for a moment.
Yeah, no problem. Thank you. Okay. Thank you so much for your kind introduction. So I will talk about smart manufacturing of ceramic fuel cells. So before I start, I like to thank all my collaborators, all the funding sources which support our research, which includes Research Council of Finland, Business Finland, and Europe Horizon that supports our research. So I come from Tampere University from Finland, and Finland is the happiest country in the world. And I also like to thank my research team. So this is our research team. And in our group, we work on different energy technologies. We work on fuel cells, electrolyzers, batteries, solar cells, from material synthesis to device fabrication, especially through additive manufacturing. And then we also do device modeling. So today, I will mainly focus on about green hydrogen, its production, and its utilization. So now there's a general consensus that electricity that is produced from solar and wind, it can be stored for large quantities in a long period of time by converting it into electrofuel by a device called electrolyzers. And then whenever needed, we can convert it back to electricity with a device called fuel cells. Most of our cells, they are reversible in nature. We can do both electricity to fuel production and from fuel to electricity production. So demand of green hydrogen is rapidly increasing, especially for energy application from 20 onward. But at the same time, there's a huge demand for green hydrogen for non-energy applications, for fertilizer industry, for chemical industry, for steel industry. So the demand for green hydrogen is rapidly increasing. So just for those who don't know, a brief introduction of fuel cells. A fuel cell is an electrochemical device that converts the chemical energy stored in a fuel into electricity. And in electrolysis mode, we convert that electricity, we can convert from electricity to fuel. There are different technologies of fuel cell technologies, like from PEM technology, solid oxide. I will mainly talk about high temperature solid oxide technology. There are lots of applications from few milliwatt to hundreds of megawatts application. So that was a brief intro that I wanted to give for everyone. Now let's come back to my presentation here. In my presentation, first I will talk about conventional three-layer structures that we work on. Then later I will talk about a unique single-layer cell structure. And then finally I will draw some key conclusions and talk about our next steps in our research. Okay, so let's start with conventional fuel cell structures. We all know that solid oxide fuel cell is a promising fuel cell technology. However, it requires high temperature for its operation, which causes lots of degradation issues and lots of material problems. So when we want to reduce temperature, when we reduce temperature, the performance also goes down, primarily due to limited ionic conductivity of the electrolyte materials. So there's a huge demand for reducing operating temperature of these devices. There are three approaches to do that. One approach is to decrease the thickness of your electrolyte. The other approach is to improve the ionic conductivity of your electrolyte materials. There are three ways to improve the ionic conductivity. One way is that you use gadolinium-doped ceria-based materials. The second approach is that to use proton-conducting materials. And the third approach is to use composite electrolytes. So these are three ways to improve the electrolytes. In our group, we work on cell fabrication, and we use different cell structures. We work on electrolyte-supported cells. We also make anode-supported cells. And now we also started working on metal-supported cells. And for these cell structures, we use oxide conductors. We also use proton conductors, and also their composites. But today, due to shortage of time, I will mainly talk about electrolyte-supported cells, where we do electrolytes manufacturing through 3D printing, and then we prepare our electrodes through inkjet printing. So here you see we prepared our electrolyte supports by 3D printing, and there we have our functional material. We prepare its electrolyte, lots of mixing, we print it, and then we do the post-processing that involves debinding steps, sintering step to make it intense and densify, and then they are ready. We have to make sure that the particle size distribution is way below the nozzle size, otherwise it can clog. So when we are preparing our paste, we just make sure that the particle size are way smaller than the nozzle size. Then once the electrolytes are ready, we prepare our electrodes by inject printing. For that, again, we have to do the ink formulation, and we have to calculate some numbers, Weber number, and also this Ronald's number. The quality of an ink is evaluated by this Derby's diagram. If in the Derby's diagram on the x-axis, we have Ronald's number, on the y-axis we have Weber number. If your ink fall in the green region, it means that it has good ink printability. So in this particular case, I'm presenting our inks. So first of all, we have to make sure that our inks are way smaller than, they're smaller than the nozzle size. Then they should have viscosity, which is acceptable. So here you see the 3D printing, inkjet printing of our electrodes. And here you see the Z number for our inks. They all fall in the green region in here. So they all have good ink printability. So there we see 20 layers of printed layers, and there we have 50 layers. So this is how the cell look like after printing. When we make our cells and we try to measure them electrochemically, with these cells we found performances about 938 milliwatt per square centimeter, and by different configurations. These cells are stable, so we have tested them on like a different long-term stability test. So these cells have demonstrated long-term stability testing. So that was a quick overview of our cells for 3-layer cells. Now I will talk about single-layer cell. The first question is, what is a single-layer cell? Basically, all the electrochemical devices, fuel cells, electrolyzers, they consist of 3 layers, anode, cathode, and electrolyte. We are also working on a unique design which is called single-layer cell, and the single layer does all the function. And the performance is up to 1 watt per square centimeter. We can report that performance. The main advantage of this cell structure is that we have simplified system design and lower manufacturing cost, and at the same time improved thermal stability. Because in 3-layer cells, when you have materials with different thermal expansion coefficients at high temperature operation, you causes lots of thermal stresses in the cell. However, with the single-layer cells, we avoid all those problems. So here you see additive manufacturing of our single-layer cells with extrusion printing. So there we prepare our inks, we do their printing after optimizing their rheological properties. Then we do the post-processing that involves debinding steps and also the sintering step, and then the cells are ready. So this is how the microscopic pictures look like. The cells are quite dense, elements are quite uniformly distributed on the cell. And then the interfaces are super important for these. So here you see like we do this 3D tomography on our samples, and we try to study how the interfaces are, because it's very important for these cells to block electronic leakage, because in the single layer cells we have to prevent the short circuiting of the cell. So these interfaces are super important. So we engineered the band levels, energy levels, and we optimize those materials. So after printing, we do the sintering step. Since single layer has to function as an electrolyte and also as an electrode, we have to find the right porosity, because if the cells are very dense, then the electrode processes suffer. Similarly, if the electrodes are very porous, then there is a danger that the gases can cross over. So we do a systematic study to find the right densification. So we print our cells with 17 millimeter diameter on the lab scale, and then we do sintering at different temperatures. So when we increase the sintering temperature, there's more shrinkage of the cells. So what we found out here is like the cells which were sintered at 900 degrees, they gave us the best performance. Another issue for the cells manufactured by additive manufacturing is their mechanical stability. So the mechanical stability of our cell is quite promising. So we add some materials inside, some additives inside that improve the mechanical stability in there. So by this processing, we achieve reasonably good mechanical stability and also good electrochemical performance. So here's the electrochemical impedance spectroscopy data of our cell. single layer cells. These cells suffer from high polarization losses, mainly because of low surface area. The cells are quite stable for the short-term stability testing that we have done for 200 hours. However, the cells suffer from these high polarization losses. To overcome them, we fabricate our cells with different structures. We fabricate the single layer cells and we add some porous layers on both sides of the cell to improve the surface area. And what we found there is like when we add this surface area, the performance improved by 32% for oxide conductors. So here the materials that you see, porous layers, they consist of the same material, but they have better porosity. So we get this improvement of about 32% enhancement in the performance. For proton conductors, ceramic materials, we get an improvement of 17% improvement in the performance when we add porous layers on both sides of the single layer. So when we do the complete cell fabrication, we get performance about 801 milliwatt per square centimeter at 550 degrees. So this is the best performance that we found from the single layer cells. So 801 milliwatt per square centimeter. And these cells are reversible. We are also operate them in electrolysis mode and produce hydrogen. So those results are not shown here. So next, I would like to briefly talk about our next steps in research and also talk about our commercialization project. So let's start with this. So first of all, I demonstrated that 3D printing and inkjet printing are suitable for solid oxide and ceramic fuel cell fabrication. The key challenge for these technologies is basically the ink formulation and the fabrication steps. Then we have to optimize the device limiting performance factors. For different structures, the device performance is limited by different processes. So we have to overcome them. But in order to commercialize this technology, the long-term stability is very important. In order to improve this long-term stability, understanding of degradation mechanisms is super important. So also I like to encourage you to, like I'm associate editor in Wired's Energy and Environmental Journal. So if you are working on energy technologies and if you are working on a review paper, so you can submit in that journal. And then I would like to talk about our commercialization project. So we had a breakthrough in our research 2 years ago regarding smart cells that can operate in both modes. So in electrolysis mode, we can produce green hydrogen, and fuel cell mode, we can produce electricity. And that we have protected and applied for pre-commercialization project that was funded by Business Finland. And now we are working on its pre-commercialization. So the project started last year and will continue till next year. And in the project, we are doing two things, like we are doing the proof of concept and developing the business model. So basically, the main idea of the project is that we all know that we need renewable energy, we need solar, we need wind. But the problem is that if we want to store electricity for a long period of time in large quantities, we cannot store electricity in batteries, way more expensive. So battery is not a good solution. And now there is a general consensus that we should store excess electricity in the form of green hydrogen or some chemical form. And whenever needed, we can convert it back to electricity with the help of a device called fuel cell. Our cells are reversible in nature, so they can do both functions, electrolysis and also fuel cell. There are already existing market solutions. However, they are expensive and they use critical raw materials like cobalt, nickel, platinum, iridium. However, the demand of these cells, especially electrolyzer cells, is rapidly increasing and estimated to be about, market size is to be about $150 billion by 2030. So here you see the complete value chain for materials to device, cell fabrication to system manufacturing, and then the final application. So our main value proposition is that our cells are basically lower cost than the existing market solution. Our performance are better than the existing market solution at lower temperature. And since we use additive manufacturing for our cell fabrication, our cell has flexibility in cell design. We can do tubular cells, we can also do planar cells. And also, we don't use any critical raw material. So basically, here you see, like, behind our innovations, we have 10 years of research. Then currently, we are working on a pre-commercialization project. And we are planning to start our company next year. And at the moment in the project, we are seeking about 3 million euros. And basically, there's already traction from our project, which is like from stack manufacturers, from space application, and from maritime application. This is our team for this commercialization project. So me and Professor Peter Lund from Aalto University, Finland. So we both are inventor of this technology. Chandra Pandey here, she is our commercialization expert, and then we have other researchers in our team. So with that, I'd like to thank you for your attention, and I'll be very happy to answer your question. Thank you.
Thank you very much for your presentation. 네, 감사합니다. 혹시 질문이 있으신 분께서는 자리에서 손을 들어주시면 감사하겠습니다. 네, so we don't have questions from the floor, so now please return to your seat. Thank you very much once again. 네, 감사합니다. 네. 템페레 유니버시티에서 진행하고 있는 다양한 프로젝트들도 알아볼 수 있었는데요. 그럼 이상으로 테크토크 토픽 2 세션을 마치겠습니다. 잠시 후 오후 1시 30분부터 이 장소에서 토픽 3 Breakthroughs in Hydrogen Production Techniques 세션이 이어서 진행이 될 예정입니다. 참가자 여러분들께서는 즐거운 점심 식사하시고 다시 이곳에서 뵙도록 하겠습니다. 1시 25분까지 다시 입장해 주시면 대단히 감사하겠습니다. 즐거운 점심시간 되십시오. 감사합니다.
The shift towards a decarbonized society is accelerating. H2 represents hydrogen and humanity, the two main pillars of Hyundai's hydrogen business, leveraging the group's wide-ranging capabilities in various sectors beyond automobiles. Hyundai's H2 vision spans across the entire hydrogen value chain, from production to its utilization across industries. Hydrogen fuel cell technology brings significant advantages, like extended range and fast refueling capabilities. The H2 fuel cell system, created through more than 20 years of research and development, represents Hyundai's commitment to creating a new wave for a hydrogen society. Clean energy based on hydrogen, paving the way for a sustainable future.
When you think about net zero aspirations, you need lower carbon systems that can work in the process and the heat that we need to work with. Hydrogen, from that perspective, is a very versatile molecule in the energy transition. It has applicability in the transport sector, especially in heavy-duty transport, where we can use it with existing combustion engines or with fuel cells. But it can also be used as a direct combustible fuel in industrials like cement and steel. These are big investments, and they offer big potential for lowering risk and carbon intensity for all kinds of consumers and companies. Chevron is uniquely positioned to lead the way forward.
We're a fully integrated energy provider enabling new energies for a growing world. And because we are Chevron, we have an opportunity to lead the way.